Alright, I've had some requests to do some examples of how to do Bode plots by hand. I know some of you have struggled with that. So we're going to start with this example, and I'm just going to work through several examples. We'll look and see how they change as the patterns in the transfer function changes. So I'm going to start with this transfer function here, and let me go ahead and draw out my axis. My horizontal axis is omega in powers of 10, and I often put a vertical axis at 1. That's not required. If you look in textbooks, you'll sometimes see that they draw their Bode plots as a square and they put their axis on the far left. But also remember, the horizontal axis is a log scale, and so it's not ever going to go to 0. This vertical axis is going to be the magnitude of h in dB. So we have omega in radians per second as our horizontal axis, and we have dB as our vertical axis. So the first thing to do in every Bode plot, independent of what the transfer function looks like, is to determine what is the low frequency asymptote. And the reason is that Bode plots build. If you remember from the video where we discussed a little bit of the theoretical aspects of this, what we do first is we substitute j omega for s. We then take the magnitude of the transfer function, and then we take the log. And because we have products and quotients, basically the log converts those to sum and difference. And the terms at higher frequencies don't enter in until we near that frequency. So we'll come in and we'll go ahead and label our what we call critical points, which are the poles and zeros of the transfer function. So we have one at 20, and that's a pole, so we'll put an X. That's 20, and then we have one at 500, also a pole, so we'll put an X. Okay, so the poles and zeros of the transfer function are negative numbers. I know that. So your pole would actually be at negative 20 and negative 500. But you got to remember that the poles correspond to cutoff frequencies or critical frequencies in the frequency domain. And so after we substitute j omega, take the magnitude, etc., and solve for cutoff, we find that those correspond to the positive values of what would be negative poles. So that's why we're able to plot those as positive frequencies. It has to do with the j omega substitution for s and the j squared putting in a negative number. Okay, so whenever you don't have, so the question to ask for finding the low frequency asymptote is there a pole or a zero at 0? The answer here is no. We have no roots of the transfer function, numerator or denominator, at 0. So that means that the slope up until you reach your first critical point is flat. So the low frequency asymptote has a slope of 0 dB per decade. Okay, now at the first critical point that I encounter is 20, and it is a pole. So poles subtract 20 dB per decade from the slope, and zeros add 20 dB per decade to the slope. Okay, so all I have here are poles. So when I get to the first pole, my new slope of the transfer function is 0 dB per decade, which was my original slope, minus 20 dB per decade, which is what the contribution of this term will be. So let me try and do that. And that's going to apply until I get to my next critical point. So I could almost, if I wanted to, just as kind of a guide to the eye, could almost put some lines here that indicate at what point I'm going to have a change of slope in my Bode plot. Okay, so now continuing at 500, I encounter another pulse. So this slope was minus 20 dB per decade. Now when I reach 500, I'm going to encounter another pole, which means I'm going to subtract an additional 20 dB per decade here. So from here forward, minus 40 dB per decade. And I have no more poles or zeros, so I will have no more slope changes. Now, the only thing that remains to be done, two things. One is I need to come in and I need to sketch the actual plot, because these are asymptotes. And so, let me fix that. So while the Bode plot approaches the asymptote, it approaches it asymptotically. So you never quite touch it, but certainly you get infinitesimally close. Alright, so this is my approximation. The only thing that remains to be done is we have to figure out the gain. We have to figure out the labels on the vertical axis. So in a case like this, where we have a low frequency asymptote, the easiest thing to do is so what we're doing here is we're trying to calculate the vertical location of our plot. So what we want to do is, in this case, so if you have zero slope at low frequency, let S go to 0 in H of S and convert to dB. So at omega getting very small, the magnitude of H is approximately 1,000 over 20 times 500, which is 1,000 over 10,000, or 1/10. And so to calculate the gain, take 20 log of 1/10. And so that is the low frequency gain. Why low frequency? Because we let omega go to 0 to get an approximation. So that's, or we let S go to 0. S being j omega. When S goes to 0, j omega goes to 0, omega goes to 0 means we're approaching DC. So we're on the low frequency end. So the log of 1/10 is 0.1. So that would be 2 dB at low frequency. So now if you come up here to your plot, what is low frequency? Low frequency is an order of magnitude or more below your lowest polar zero. So we had one at 20. So as long as I come down here to about 1.5 orders of magnitude, so I can put a tick mark right there and call that, let's go back to black, I can call that 2 dB. Now, if you want to tick this off in units of 20 dB, so right here where I had my horizontal line is minus 18, minus 38, and so on. So there's that. Now let's look at phase. So I have, once again for phase, I want to start at the low frequency end because my phase is also additive. So at the low frequency end, I have no poles or zeros at 0. At S equals 0. So at very low frequency, I've just got a constant. So my phase starts at 0 degrees. So poles contribute negative 90 in phase. Zeros contributed positive 90 in phase. I have no zeros, I have only poles, and I have 2. So let me see if I can somehow, let's go with a different color, and we'll do the phase right underneath the magnitude so that I can use the same scale. So we'll come right down here. Let's mark this off here. We'll call this 90 degrees or minus 90. We'll call this minus 180, and we'll call this 0. So this is our phase plot, and this is omega, and I have the same points. So coming up to my first break point, or my first critical point, I'm at 0 degree phase. Let me once again use a different color. We'll do orange. So I'm at 0 phase. When I get to my first pole, I drop by 90 degrees in phase. When I get to my second pole, I drop by another 90 degrees in phase. So the phase plot always looks like stair steps. You'll always cross over in the middle of the step. The asymptote is longer than it is for the magnitude plot, so it breaks from the asymptote sooner. To me, it is a little more difficult to sketch a phase plot by hand, but roughly this pink line gives you an indication of phase. Obviously, I would show a more dramatic shift if I had my axis bigger. I just kind of messed up and didn't leave myself enough room to do a phase plot. Alright, so I'm going to stop the